We've spent all summer long looking through these slides from 100 years ago, analysing images taken by previous generations of telescopes. But now it's time to move forwards and see how the tools we use to view the universe have changed since these were taken. It feels like I've spent quite some time looking through these amazing images, each with their own story and offering a glimpse into a completely different era of astronomy. But what have been the biggest changes and improvements since then? Probably the most important telescope in our collection of slides is the Hooker telescope. With a diameter of 2.5 meters, or 100 inches for those of us working in old money, it was the largest optical telescope in the world from its completion in 1917 until 1949. Edwin Hubble himself used this telescope to discover the first Cepheid variable in Andromeda, which gave him the information to realise that it existed beyond the Milky Way and was therefore a galaxy in its own right. If you don't know why this was important, then please go back and watch our video on why it took so long for astronomers to realise that galaxies existed from a couple of weeks ago. Having a larger diameter to your telescope is useful for two main reasons. Number one is the light grasp. The bigger your objective lens or mirror, the more light your telescope can collect. The light grasp of a telescope is directly proportional to the area of the objective, so that means that it has a squared proportionality with the diameter of the telescope. So, if you double the diameter of a telescope, you can actually see 4 times fainter objects. The second reason this is useful is to do with the smallest angle of the sky that you can detect with your instrument, which is determined by the angular resolution. If you've got a sense of déjà vu on this equation, it's because we featured it in last week's video too. Thanks for watching. It is the Rayleigh's criterion equation and tells us that the angular resolution is inversely proportional to the diameter of your telescope. So again, if you double your diameter, then your telescope can resolve objects that are half as far apart and still see them as separate objects. The current largest single dish optical telescope has a diameter of 10.4 meters and is the Gran Telescopio Canarius. But it should be superseded by the end of the decade by the brilliantly named Extremely Large Telescope, or ELT, currently under construction in Chile, which will have a diameter of 39.5 meters. It wasn't until 1800 that we realised there were types of light we couldn't see with our own eyes. I've unfortunately not got time to go into the experiments that led to this, but it is really cool, so after this video, have a look into it. We gradually learnt about more types of light until we filled in the whole spectrum, but we weren't able to observe anything in space other than visible light until the first radio observations in 1931. We've had other big steps forward in observing different wavelengths, particularly in the 1960s and 1980s, and now we can observe the light emitted or reflected by objects in space across pretty much most of the electromagnetic spectrum. If you're curious as to why this matters, take a look at the Lagoon Nebula here. It looks fantastic in visible light, but the dust and gas that makes up the nebula actually blocks much of what is behind. So if we switch to infrared, then suddenly we no longer are having our view blocked by the dust and gas, and we can see the multitude of stars and galaxies that were previously hidden behind. This isn't just for distant objects though. Looking at the sun through the whole spectrum of light, we can see how different features of the star become more or less prominent in different wavelengths. This then allows us to develop a more complete understanding of its inner workings than just looking at it in visible light could ever allow us to do. One problem though, not all wavelengths of light can pass through the entirety of Earth's atmosphere, which means that we need certain types of telescope to escape to the one place that hasn't been corrupted by capitalism. Even in the visible part of the spectrum, the atmosphere absorbs and scatters light as it passes through, making it preferable to mount telescopes at higher altitude and reduce the amount of atmosphere between you and what you are observing. This is one of the reasons that the Hubble Space Telescope has been taking such high qualities during its 35-year history, despite having a smaller diameter than several other telescopes observing in the optical range on Earth. And for gamma, X-ray and ultraviolet, along with parts of infrared, the only place to actually observe the universe in these wavelengths is to have your telescope in space. There are challenges to this though, which we covered in the Why Don't We Put Telescopes on Top of Mountains video earlier this year. As such, we don't put all telescopes in space, and have not attempted to put longer wavelength radio telescopes in space. Reason for this is that to get a decent angular resolution on them, they would need to be absolutely massive and therefore wouldn't be a manageable payload for most spacecraft to launch into orbit. Switching from photographic slides to digital detectors such as CCDs has been another massive upgrade for astronomers. This is for a number of reasons, but I'll narrow it down to just 3 for this video. 1. Quantum efficiency, which we touched on in the exposure time episode, tells us what percentage of incoming light is detected by different types of detectors, with the human eye at 1%, photographic film getting up to around 4%, and CCDs able to detect in excess of 70% of incoming light. This can allow for shorter exposure times to get the same results, and seeing fainter and therefore further if we use the same exposure time. With a CCD, you can get a live view of what your telescope is looking at, allowing you to adjust the settings before taking any images. If you're working with photographic film, they had to manually set up each shot and wouldn't necessarily know if they had any issues with the focus or anything else until the images had been processed. And 3, by producing digital images, these can be shared online without the loss of quality that you'd get if you were scanning old-style photographs. This is crucial for the astronomical community, as it means that NASA and other organisations can make all their observations public, allowing others to trawl through the data and spot trends that might otherwise be missed. It's also meant that a fair few years ago now, I was able to access maps of the entirety of the planet Mars. And this then meant I could analyse rampart craters, which suggested that the surface of that planet was less dry than it is today. If I had to take these images myself, then I simply wouldn't have been able to do the project. I wouldn't have been able to get enough high quality images, and the range that I'd be working from would mean that the resolution would be way too low. For every image in this collection, the illustration or photograph was taken from Earth. But with advances in rocket propulsion, we've been able to have satellites equipped with a range of detectors and telescopes in orbit of other planets and moons across the solar system. The benefit of this is easy to understand. By getting closer, we gain a much better view of the finer details, in the same way that if you compared what you could see about a person from 200 metres away versus 20 centimetres away, then the increase in detail and lack of personal space would be astounding. Also, if you are in orbit around a planet or moon, then you can actually view the entire surface of it over the course of multiple orbits. This can allow you to map whatever the satellite is orbiting around and not just be limited by which way your observatory and your subject are pointing when you want to make your observations. No, I'm just scratching the surface here and had to skip a few major milestones and cut down at least 2 tangents that this video is going to go on just to make it kind of fit to time. If you're interested in learning about more of these advances though, then I would suggest looking into adaptive optics in astronomy. That one's really cool, and how using 2 or more telescopes together for interferometry can really boost the angular resolution of a group of telescopes. And that wraps up our summer slide series for 2025. I really hope you've enjoyed this selection of videos, and it's helped to keep those little grey cells active over the summer holidays. Next week, I'm going to be back in the lab, and more importantly, I'll be revealing what topic of astronomy we're going to focus on for the second series of Watch This Space, along with answering a random astronomy question from the comments of one of our previous videos. Please do give this video a like if you've enjoyed it. Let us know if there's anything you feel we've missed in our overview of telescopic improvements in the comments. And please do subscribe to our channel for more weekly content on astronomy. As ever, until next time, please continue to watch this space. Thank you.